The earlier two lectures on magnetic field in material, we have introduced the concept of free and bound magnetizing currents and introduced the magnetization vector. And in the last lecture, we have following an intuitive approach, we have established a relation between the magnetization current density with the magnetization vector through a curl relation. And as we have pointed out there, that the calculation that was presented was not mathematically rigorous one, and it lacks one term, that is the coming from the surface. Here we shall consider the situation in a mathematically rigorous way. Let me first describe the problem. We have a magnetized material which is within a volume V prime bounded by a surface S prime. We consider a volume element dV prime macroscopic volume element, which is located at R prime, and our aim is to find out the field at a point R. At P having position vector R, the field coordinate, and it is the relative coordinate R. And since this material is distributed over atomic dimension, we choose our coordinate system in such a way that small r is much greater than r prime, so that if we expand 1 by r in binomial series, it is sufficient to keep the first two terms. So this was to say that 1 by r is equal to 1 by r1 cos theta. It is where theta is the angle between these two. The first term leads to the monopole contribution to the potential, which is 0 for magnetism, and second term leads to the dipole contribution. So as to say, we treat the the BM or the field at an external point due to magnetized material in dipole approximation. It was found during the calculation of vector potential that it is not very easy to calculate vector potential, as we found that in electrostatics calculation gets highly simplified through the introduction of the potential, but in magnetism introduction of the vector potential does not simplify the calculation too much, because in most of the cases the vector potential itself does not exist, but the corresponding magnetic field has a finite value. The utility of vector potential will be clear here. Whenever we want to describe the magnetized material under this approximation, the magnetized material can be treated in dipole approximation. So if we want to follow the vector potential approach, the dipole concept comes into play and becomes very helpful. And if we adopt scalar potential approach, then also the magnetic dipole concept is found to be very helpful. Now come to the external point. Our concept is that, our assumption is that we have a space in which a limited portion has been occupied by the magnetic material. There may be some conductors too, but the field point is in vacuum. So we designate a point within the vacuum where we want to calculate the field. So far the external point is concerned, here there is no current at the field point. So since there is no current, we can define scalar potential. And we shall firstly consider this, and will land up to the pole concept, that is the concept of permanent magnets, North Pole and South Pole. But whenever we want to apply the scalar potential approach, or so-called the pole formalism at internal point, the calculation fails, in the sense it leads to erroneous result. The reason is that within the magnetized material there are bound currents, so the current density is not zero, so one cannot define scalar potential within the magnetized material. Other alternative approach is that the vector potential approach. The vector potential approach is applicable at external as well as internal point too, because it is guided by the law that divergence P is zero, which is a universal law of magnetism. So the vector potential approach is valid at internal and external points, and the vector potential approach leads to the concepts of equivalent current, of which we have one already encountered. Jm is equal to curl of M. This is the equivalent current formalism. So with this introduction we shall start calculating the magnetic field due to a magnetized material, firstly adopting the pole formalism. So B at an external point or remote external point, it is remote external point means the dipole approximation is valid. One is scalar potential approach. Pole concept. So the situation is this: the dipole moment of the volume dV is the dipole moment of the volume dV can be calculated is that. So this is dm is equal to dipole moment of delta V prime. Now first thing is that we know the magnetization over here is M at R prime dot times dV prime. This is the dipole moment. If we want the find out the corresponding scalar potential at P, the scalar potential at P is equal to 1 upon 4 pi delta M dot R upon R cube. So this is equal to that the divergence of 1 by R is equal to plus R by R cube. So R by R cube term has been adjusted here. In other words, this is the solid angle subtended by this volume element over there. If we look at it, it will be in a plane, a surface area, and that surface area holds a solid angle. But we have written this result in a some other different form which will facilitate interpretation. It is 1 upon 4 pi. We write this part as it will have two terms. One is this, and the other term is here dv prime was missing. The vector identity that I have used is divergence of phi times a. Phi times a is equal to phi times divergence of a times grad phi times a. In our original calculation, this term was there, so I have written this equal to this minus this. Now, what is the total scalar potential at R? Scalar potential at R is obtained by integrating d phi m over source so to say this is on simplification of this part. This sign should be minus as it has to be subtracted. To the first term, we can use divergence theorem to convert it into a surface integration. So let me convert the first using the divergence theorem into a surface integration. So the result is 1 by 4 pi, where S prime is the closed surface bounding this. It is the as usual volume integration. We can write it as it is scalar where we have introduced the magnetization pole densities. Magnetization pole densities sigma m at R is the unit normal vector. So this is the surface magnetization pole density and this is the volume magnetization pole densities. Compare these with the relation sigma p is equal to p dot n and rho p is equal to minus divergence p as we have obtained in dielectrics. Now the one thing, note that I have not used primes as stated earlier. They are the field equation. If we use them within the integral, then prime will be used, otherwise it is not at all required to use primes. So we found that the potentials are 1 by R potential, that is Coulomb type potential, 1 by R potential. And these are the surface and volume densities of the magnetization magnetic pole densities. Now if we could start with this equation and this equation, there is no more approximation involved in coming from here to there. Only thing is that we have integrated But the fact is that this expression facilitates interpretation of the result in terms of pole densities, which this does not. So we have translated the same equation from one form to another form to get a form which facilitates physical interpretation. So we have introduced pole densities, and it is very easy to verify that the total magnetization charge or pole is 0. To get it, we must integrate it over the surface and this over the volume, and if we convert one into the other, then we find that the net pole density is 0. Similar thing we also obtain in the case of polarization charge. Since the net polarization charge is 0, the contribution coming from the surface and volume was 0. In this case, it is sigma m ds prime over s prime plus sigma rho m dv prime over v prime is 0. The corresponding situation in electrostatics was so this development is found to be very similar to that obtained in magnetostatics. Now the problem is how to calculate the field. Now let me first write the potential. This magnetic potential at R is 1 by 4 pi Now to find out the field, corresponding field is obtained by the definition of scalar potential. Bm is equal to minus mu 0 phi m. So the result is minus mu 0 upon 4 pi. This is the grad operation, double operation with respect to the field coordinates. So this is with respect to the field coordinate, and integration is with respect to the source coordinate, so we can interchange the order. And furthermore we know that nabla does not operate on it, it's 0, so it operates only on 1 by r, and nabla operating on 1 by r is simply minus r by r cube. So this minus r absorbs this sign, so we get plus. This is simple application of Coulomb's law of magnetostatics. That is, we have a distribution of poles over volume and over surface. This is the field, inverse square field at an external point due to the surface density of poles, and this is the field due to the volume density of poles. Let us apply this to a known situation. We have a bar magnet, which is a magnetized uniformly. If we consider this is the z-axis, in that case magnetization is uniform k cap m. Now, what is the the unit vector? The unit vector is in towards the left, and this is towards the right. So sigma m over here is simply minus m, because this is equal to minus k cap and this is equal to plus k cap. So this is known as south pole, and sigma m is equal to plus m over here. It is at point A, this is at point B. Sigma m at A and sigma m at B is equal to plus m. So this is the north pole. So this is south, this is north, and the magnetization is in this direction. And if we consider volume's contribution, this is is 0. So there is no volume density, volume poles. Only thing will happen that near the ends the magnetization is not uniform. Near the ends the magnetization will be this is uniform over this within the bulk, and near the end the the magnetization will be slightly non-uniform due to the end effects, and which causes a contribution coming from there, and which shifts the pole right from the surface to a bit inside, and similarly this. So we see that the scalar potential approach reconciles with our concept of magnetic poles that we were habituated with in the case of permanent magnet. Let me now do the same calculation in the vector potential approach. Concepts of current. The dipole moment of V prime is as stated earlier. So the magnetic vector potential at P due to this is mu 0 upon 4 pi delta m cross r upon r cube. For delta m we write this, and r by r cube has written in this form. Now consider this term, curl of m by r. This is equal to 1 by r curl of m plus grad of 1 by r cross m. Here we have this term in a reverse order, so that we can write uh, this is the vector identity. So if we write this is the term we have or not original, so we write it as this is the expression. You see that we have this term, we have used this by identity, and then finally this term becomes this minus this. So then what is the total vector potential? Total vector potential at A, at P, total potential at R or at the field point is the dA over the source. That is to say mu 0 upon 4 pi integration over V prime this term, this volume element can be converted into a surface element. We know the alternative form of Stokes theorem is that original divergence theorem is that A dot ds is equal to divergence A dv. It is over V, it is over closed surface S. If we use A to B C cross B, where C is an arbitrary constant vector, then the left hand side becomes C dot B cross ds, and the right hand side is divergence of A is equal to divergence of C cross B, and this is can be written as minus C dot curl B. So the result is minus C dot volume that is to write that curl of B dv volumeal integration is equal to pen doesn't work well. This is equal to closed surface integration ds cross B. This second term is in this form with a minus sign, so we can write it as this is the volume part. And this will be a surface part. ds comes earlier, but this due to the minus sign I have interchanged the appearance of these two. So this can be written as This is the surface part. Where this Jm is equal to Jm at R is equal to this part, curl times M at R, and J is the surface contribution. Jms at R is equal to n cap. The direction is taken within this. In our earlier class, following intuitive argument, we got this, but we missed this. This was not there. So that is what we were talking about, that the derivation made in the earlier class is not mathematically rigorous one. So we have introduced equivalent current formulas. These currents are this. If we know the magnetization, we can find out the volume and surface densities of magnetization current, and we come across to the vector potential. Note that this is the dipole contribution, so the entire calculation is in dipole approximation. So what is the corresponding field? The corresponding field is simply this: Bm is equal to curl of M, which we will better write as M magnetization. So we need to curl it again. This is with respect to the field coordinates. So this is first step is mu0 upon 4 pi we interchange the order of integration and differentiation, and the differentiation on the operating on this current densities gives 0, because they are the function of field coordinates as source coordinates, and these are the differentiation with respect to field coordinate. So curl operates only with this, and the curl of then we know that curl of phi cross A is equal to two terms. You will have phi times curl A, which is 0 here, plus grad phi cross A. This part will contribute, and this is minus R by R cube. And if we adjust this to the ordering, if we adjust the ordering, it will be this is exactly the application of Biot-Savart law to find out the field at an external point corresponding to the volume current density Jm and surface current density Jms. So the problem of finding out the field at an external point has been reduced to knowing the current densities or the pole densities. If you know this, then the standard technique as applied to the magnetostatics in vacuum can be applied to find out the field due to magnetized material. To end this, we shall take an example and a simple example and calculate the corresponding pole and current density. We consider an uniformly charged pair and uniformly magnetized pair. We consider an uniformly magnetized pair of radius a. This is the sphere. This is the direction of magnetization m. We considered it is to be the z-axis, so magnetization is k cap m, and this is the coordinate system used. This is the origin. So the pole density, come to the pole density. Sigma m is equal to m dot n cap. In this case it is m dot r cap on the surface. So this is equal to k cap m dot I cap sin theta cos phi plus j cap sin theta sin phi plus k cap cos theta. So this is equal to simply m cos theta. You see that it is the pole sigma m is equal to plus m over here, sigma m is equal to minus m over here, because here theta is 0, cos theta is 1, here cos theta is pi and cos 9, and on the equatorial plane the pole density, surface pole density is 0. The volume pole density m is 0 as capital M is a constant vector. Current density. The surface current density is defined as m cross n cap, which is m cross r cap. So this is I cap, k cap m cross I cap sin theta cos phi plus j cap sin theta sin phi plus k cap cos theta. So this k cross I is minus j, so this is minus j cap sin theta cos phi, and k cross j is, this is plus j, k cross j this is plus j cap, because k cross I is j and this is minus I sin theta sin phi, and the rest term is 0. If we take sin theta common, m sin theta, and the rest term is phi cap. So this is the current density, and again the volume current density is curl of m. Since m is a constant, it is a null vector.